Descriptive statistics is a fundamental branch of statistics that focuses on summarizing and presenting data in a meaningful way. Today, we'll explore how descriptive statistics applies specifically to grouped data. Descriptive statistics serves a crucial purpose. It takes raw, unorganized data and transforms it into clear, understandable summaries. Rather than looking at thousands of individual data points, descriptive statistics helps us see the big picture through measures like averages, ranges, and distributions. Consider the difference between raw data and organized data. On the left, we have individual data points scattered without clear structure. It's difficult to identify patterns or draw conclusions from this format. On the right, we see the same data organized into groups or classes. This grouped format immediately reveals patterns. We can see which age ranges are most common and how the data is distributed across different intervals. Grouped data is simply data that has been organized into intervals or classes. Instead of working with individual data points, we group similar values together. This process makes large data sets much more manageable and helps us identify trends that might be hidden in raw data. Grouped data offers several key advantages. First, it simplifies large data sets by reducing thousands of individual values into manageable categories. Second, it reveals patterns and trends that might be invisible in raw data. Third, it enables us to perform statistical calculations more efficiently. Finally, it improves data visualization by creating cleaner, more interpretable charts and graphs. Grouped data is everywhere in real-world applications. Age distribution groups people into meaningful life stages like children, young adults, middle age, and seniors. Income brackets help economists and policymakers understand economic distribution across different social classes. Educational institutions use group data for test scores and grade distributions, while businesses analyze customer feedback through rating groups. These examples show how grouping transforms complex data into actionable insights that drive decision-making across various fields. Understanding descriptive statistics for grouped data is essential for anyone working with large data sets. It provides the foundation for more advanced statistical analysis and helps us make sense of the world through data-driven insights. A frequency distribution is a fundamental tool in statistics that organizes raw data into meaningful groups called class intervals. It shows us how often values appear within each range of our dataset. Let's start with a definition. A frequency distribution is a table that displays how frequently data values occur within specific ranges or class intervals. Here we have 20 test scores ranging from 45 to 94. In their raw form, these numbers are difficult to analyze and interpret. We organize this data by creating class intervals. Each interval represents a range of values. Here we've created 6 intervals, each spanning 10 points. Now we create our frequency distribution table. The left column shows our class intervals, and the right column shows how many data points fall within each interval. Let's examine the key terms used in frequency distributions. Understanding these concepts is essential for working with grouped data. Class width is the range covered by each interval. For the interval 70 to 79, the class width is calculated as 79 minus 70 plus 1, which equals 10. Class boundaries are the precise mathematical limits of each interval. For 70 to 79, the boundaries are 69.5 and 79.5, eliminating gaps between consecutive intervals. The class midpoint is the center value of each interval, calculated by adding the lower and upper limits and dividing by 2. For 70 to 79, the midpoint is 74.5. When creating class intervals, we generally prefer equal intervals because they make analysis and interpretation easier. However, unequal intervals may be necessary when data is highly skewed or when certain ranges require more detailed examination. Frequency distributions transform raw data into organized, interpretable information. By choosing appropriate class intervals and understanding key terminology, we create the foundation for all subsequent statistical analysis of grouped data. When working with grouped data, we need a special approach to calculate the mean. Since we don't have individual data points, we use the frequency and midpoint of each class interval. The formula for calculating the mean of grouped data uses the sum of frequency times midpoint divided by the total frequency. Here, Fi represents the frequency of each class, and Xi represents the midpoint of each class interval. We use class midpoints because they represent the center value of each interval. This assumes that data points are evenly distributed within each class, giving us the best estimate when we don't know the exact individual values. Let's work through a complete example. Here we have a frequency distribution table showing class intervals, their frequencies, midpoints, and the product of frequency times midpoint for each class. Notice how each midpoint is calculated as the average of the class boundaries. For example, the midpoint of class 10 to 20 is 15, and the midpoint of class 20 to 30 is 25. Now let's calculate the mean step by step. First, we sum all the Fi times Xi values. 75 plus 200 plus 420 plus 270 plus 220 equals 185. Next, we sum all the frequencies. 5 plus 8 plus 12 plus 6 plus 4 equals 35. Finally, we divide the sum of Fi times Xi by the sum of frequencies. 1185 divided by 35 equals 33.86. This is our grouped data mean. The mean of this group data is 33.86. This represents the average value of all data points in our distribution, calculated using the frequency-weighted midpoints of each class interval. Now we'll work through a complete example of calculating the mean for group data using exam scores from a statistics class. We have exam scores for 50 students, grouped into class intervals with a width of 10 points each. First, let's create our frequency distribution table showing the class intervals and their corresponding frequencies. Next, we need to calculate the midpoint for each class interval. The midpoint is found by adding the lower and upper bounds of each interval and dividing by 2. Now we'll create our complete calculation table with class intervals, frequencies, midpoints, and the product of frequency times midpoint. Finally, we substitute our values into the formula. The sum of F times XM equals 388.85, and the sum of frequencies equals 50. Therefore, the mean is 388.85 divided by 50. Median is a fundamental measure of central tendency that represents the middle value in a data set when all values are arranged in order. For grouped data, we need a special formula to calculate this middle value. For grouped data, we cannot simply find the middle value directly since we only have class intervals and frequencies. Instead, we use a special interpolation formula to estimate the median value. Let's break down each component of this formula. Each variable has a specific meaning and role in calculating the median for grouped data. The most crucial step is identifying the median class. This is the class interval that contains the median value. We find it by locating the class where the cumulative frequency first reaches or exceeds half of the total frequency. Now let's see the complete calculation process. Once we identify the median class and gather all the required values, we substitute them into our formula to find the median value for the grouped data. The mode represents the most frequently occurring value in a dataset. For grouped data, we need to identify the modal class and use a specific formula to calculate the mode. The mode is defined as the most frequent value in a dataset. For grouped data, we first identify the modal class, which is the class interval containing the highest frequency. Let's examine a sample frequency distribution. We have 5 class intervals with their corresponding frequencies. Notice that the class 30 to 40 has the highest frequency of 18. The modal class is 30 to 40 because it has the highest frequency of 18. This is where our mode will be located. The formula for calculating the mode of grouped data involves several components. Let me break down each part of this formula for you. Let's examine each component of the formula. L represents the lower class boundary of the modal class. F subscript M is the frequency of the modal class itself. F subscript 1 is the frequency of the class immediately before the modal class, while F subscript 2 is the frequency of the class immediately after the modal class. Finally, represents the class width, which is the size of each class interval. This is typically the same for all classes in a frequency distribution. This formula works by interpolating within the modal class to find the precise location of the mode. It considers the frequencies of neighboring classes to determine where exactly the mode falls within the modal class interval. Now we'll work through a complete example of calculating the mode for grouped data using our sample dataset of test scores. First, we need to identify the modal class. This is the class interval with the highest frequency. Looking at our table, we can see that the class 40 to 50 has the highest frequency of 12. Now we'll apply the mode formula for group data. The formula requires several values from our modal class and the classes immediately before and after it. Let's identify each component of the formula. L is the lower boundary of the modal class. F1 is the frequency of the modal class. F0 is the frequency of the class before the modal class. F2 is the frequency of the class after the modal class. And H is the class width. Now let's substitute these values into our formula and calculate the mode step by step. Step 2. Let's simplify the numerator and denominator separately. The numerator is 12 minus 8, which equals 4. The denominator is 2 times 12 minus 8 minus 10, which equals 24 minus 18, or 6. Step 3. Now we calculate the fraction 4 divided by 6, which equals 0.667. Then we multiply this by the class width of 10 to get 6.67. Finally, we add this to the lower boundary of 40. Therefore, the mode of our grouped data is 46.67. This means that the most frequently occurring value in our test score distribution is approximately 46.67 points, which falls within the modal class interval of 40 to 50. Variance is a fundamental measure in statistics that tells us how spread out or dispersed our data points are around the mean. Understanding variance for grouped data is essential for analyzing frequency distributions. Variance quantifies how much the individual data points deviate from the average value. A small variance indicates that data points are clustered closely around the mean, while a large variance shows that data points are spread out over a wider range. Here we can see two different distributions. On the left, we have data with low variance, where points cluster tightly around the mean. On the right, we have high variance, where data points are spread out much further from the mean. Now, let's examine the mathematical formula for calculating variance in grouped data. The sample variance formula for grouped data uses the sum of frequencies times the squared deviations from the mean, divided by the total frequency minus 1. Let's break down each component of this formula. Fi represents the frequency of each class interval. Xi is the midpoint of each class. X bar is the mean we calculated from our grouped data, and we divide by the sum of frequencies minus 1, which gives us the degrees of freedom for a sample. Now let's compare this with the population variance formula. The population variance formula is similar, but we divide by the total frequency without subtracting 1. We also use sigma squared instead of s squared and mu instead of x bar to represent the population mean. The choice between sample and population variance depends on your data. Use sample variance when you're working with a subset or sample of a larger population. This accounts for the uncertainty in estimating the population mean. Use population variance when you have data for the entire population of interest. A key insight is that sample variance uses n-1 in the denominator, known as Bessel's correction. This adjustment provides an unbiased estimate of the population variance, compensating for the fact that we're using the sample mean rather than the true population mean in our calculations. Now we'll calculate the variance for our group data using the same dataset. Variance measures how spread out the data points are from the mean. Here's our data table with class intervals, midpoints, and frequencies. We previously calculated the mean as 40.18. To calculate variance, we need to find the deviation of each midpoint from the mean, then square these deviations. Let's create a calculation table showing each step. We'll calculate the deviation, squared deviation, and weighted squared deviation for each class. Now we'll calculate each row step by step. For each class, we find the deviation from the mean, square it, and multiply by the frequency. Now we sum all the weighted squared deviations and divide by the total number of observations to get the variance. The variance of our group data is 218.23. This tells us how much the data values deviate from the mean on average. A higher variance indicates more spread in the data. Standard deviation is one of the most important measures of variability in statistics. It provides a more interpretable measure of spread than variance because it returns the measure of variability to the same units as the original data. Standard deviation is defined as the square root of the variance. This simple mathematical relationship connects these two fundamental measures of spread. The formula for standard deviation is sigma equals the square root of variance. We can also write this as sigma equals the square root of sigma squared, where sigma squared represents the variance. The key advantage of standard deviation over variance is in the units. Variance is measured in squared units, while standard deviation returns to the original units of measurement. For example, if your data is measured in kilograms, variance would be in kilograms squared, but standard deviation would be back in kilograms, making it much easier to interpret. Now let's demonstrate the calculation using a variance value from our previous section. Let's use the variance value of 25 that we calculated in the previous section. Step 1. We apply the standard deviation formula. Step 2. We substitute our variance value of 25 into the formula. Step 3. We calculate the square root of 25, which equals 5. Therefore, the standard deviation is 5. This standard deviation of 5 tells us that on average, the data points deviate by 5 units from the mean. This is much more interpretable than saying the variance is 25 squared units. Now we will calculate the standard deviation using the variance we found in the previous example. The standard deviation is simply the square root of the variance. From our previous calculation, we found that the variance of the exam scores is 156.25. This represents the average of the squared deviations from the mean. The formula for standard deviation is sigma equals the square root of the variance. This gives us a measure of spread in the same units as our original data. Let's work through the calculation step by step. We substitute our variance value into the formula. Step 1. We substitute our variance value of 156.25 into the square root formula. Step 2. We calculate the square root of 156.25, which equals 12.5. This is our standard deviation. Our final result shows that the standard deviation is 12.5 points. But what does this number actually tell us about our exam score data? This standard deviation of 12.5 points tells us that, on average, individual exam scores deviate from the mean by approximately 12.5 points. A smaller standard deviation would indicate that scores are clustered closer to the mean, while a larger standard deviation would indicate more spread in the scores. In practical terms, this helps us understand the consistency of performance in the class. Most students scored within about 12.5 points of the average, giving us a clear picture of the score distribution. Percentiles are important statistical measures that tell us the relative position of a data point within a data set. Unlike measures of central tendency, percentiles help us understand where a particular value stands compared to all other values. For example, if a student scores in the 75th percentile on a test, it means their score is higher than 75% of all students who took the test. This gives us valuable information about relative performance. When working with group data, we cannot simply count individual values to find percentiles. Instead, we use interpolation within the appropriate class interval to estimate the percentile value. The formula for calculating percentiles in group data uses interpolation. Let me show you this formula step by step, breaking down each component so you understand exactly what each variable represents. Now let's break down each component of this formula. P represents the percentile value we want to find. L is the lower class boundary of the percentile class, the class interval that contains our desired percentile. The variable P represents the percentile as a decimal. For the 25th percentile, P equals 0.25. For the 90th percentile, P equals 0.90. N is the total frequency, the sum of all frequencies in our dataset. The remaining variables complete our interpolation calculation. CF represents the cumulative frequency of the class before the percentile class. F is the frequency of the percentile class itself, and W is the class width. The logic behind this formula is interpolation. We first find which class interval contains our desired percentile, then we estimate where within that interval the percentile value lies. The fraction represents how far into the class we need to go, and we multiply by the class width to get the actual distance. This percentile formula is essential for analyzing group data in statistics. It allows us to determine relative positions and make meaningful comparisons within data sets, which is crucial for data analysis and interpretation. We'll calculate the 25th percentile, also known as the first quartile, using our exam scores dataset. The 25th percentile is the value below which 25% of all observations fall. The formula for calculating percentiles in group data involves several components. We need the lower boundary of the percentile class, the total number of observations, and the cumulative frequencies. Now let's apply this formula step by step to find the 25th percentile of our exam scores. Step 1. We calculate the total number of observations by adding all frequencies. 5 plus 8 plus 12 plus 15 plus 10 equals 50 total observations. Step 2. We find the position of the 25th percentile by multiplying n times p over 100. That's 50 times 25 divided by 100, which equals 12.5. Step 3. The 12.5th observation falls in the 60 to 70 class interval, since the cumulative frequency up to this class is 25, which includes our target position. Now we can substitute all values into our percentile formula to calculate the exact 25th percentile value. We substitute our values: L equals 60, N equals 50, P equals 25, CF equals 13, F equals 12, and H equals 10. Substituting into the formula, P25 equals 60 plus the fraction 12.5 minus 13 over 12 times 10. This simplifies to 60 plus negative 0.5 over 12 times 10. The final calculation gives us 60 plus negative 0.417, which equals 59.58. The 25th percentile of our exam scores is 59.58. This means that 25% of all students scored below 59.58 points on the exam, while 75% scored above this value. Quartiles are special percentiles that divide grouped data into 4 equal parts. Understanding quartiles is essential for analyzing the distribution and spread of data. Quartiles are specific percentiles that divide your dataset into 4 equal parts, each containing exactly 25% of the data points. Here we can see how quartiles divide the data into 4 equal sections, with each section containing exactly 25% of all data points. The quartiles Q1, Q2, and Q3 mark the boundaries between these 4 sections, dividing the data at the 25th, 50th, and 75th percentiles respectively. The first quartile, Q1, represents the 25th percentile, meaning 25% of the data falls below this value. The second quartile, Q2, is the 50th percentile, which is also known as the median. Half of all data points fall below this value. The third quartile, Q3, represents the 75th percentile, meaning 75% of the data falls below this value. To calculate quartiles for grouped data, we use the percentile formula, adapting it for the specific percentile values of 25, 50, and 75%. Here's the general formula for calculating any quartile, where K represents the quartile number, 1 for Q1, 2 for Q2, and 3 for Q3. Let me explain each component of this formula. L is the lower boundary of the class containing the quartile, K is the quartile number, and N is the total frequency. CF before represents the cumulative frequency before the quartile class, F is the frequency of the quartile class itself, and H is the class width. Now, let me walk you through the systematic steps for calculating quartiles in group data. First, calculate the positions of each quartile by dividing the total frequency by 4 for Q1, by 2 for Q2, and multiplying by 3, then dividing by 4 for Q3. Second, create a cumulative frequency column to help identify which class interval contains each quartile. Third, identify the specific class intervals that contain each quartile position by comparing positions with cumulative frequencies. Finally, apply the quartile formula to each quartile using the appropriate values for that specific class interval. These systematic steps ensure accurate calculation of all 3 quartiles, providing valuable insights into the distribution and spread of your group data. Now we'll calculate the quartiles for our sample dataset of student test scores. We have 50 students total, and we need to find Q1, Q2, and Q3. First, we find the positions of each quartile. With n equals 50, Q1 is at position 12.5, Q2 at position 25, and Q3 at position 37.5. Now let's calculate Q1. Since the 12.5th value falls in the 60-69 class interval, this is our Q1 class. Using the quartile formula, we substitute our values. L is 59.5, the lower boundary of the 60-69 class. The calculation gives us Q1 equals 65.75. Next, let's calculate Q2, which is the median. The 25th value falls in the 70-79 class interval. For Q2, we use the 70-79 class. The calculation gives us Q2 equals 73.94, which is our median value. Finally, let's calculate Q3. The 37.5th value falls in the 80-89 class interval. For Q3, we use the 80-89 class. The calculation gives us Q3 equals 82.0. Now let's summarize our quartile results and interpret what they mean for our data set. Our quartile calculations show that Q1 is 65.75, Q2 is 73.94, and Q3 is 82.0. This means 25% of students scored below 65.75, half scored below the median of 73.94, and 75% scored below 82.0. Most importantly, the middle 50% of students scored between 65.75 and 82.0. This range of 16.25 points represents the interquartile range and shows the spread of the central half of our data. The interquartile range, or IQR, is a crucial measure of variability that focuses on the spread of the middle 50% of our data. The IQR is defined as the difference between the third quartile, Q3, and the first quartile, Q1. This simple formula gives us the range that contains the middle 50% of our data values. To understand the IQR, imagine our data divided into 4 equal parts by 3 quartiles. Q1 marks the 25th percentile, Q2 is the median at the 50th percentile, and Q3 represents the 75th percentile. The IQR represents the range between Q1 and Q3, which contains exactly 50% of all data values, specifically the middle 50%. This makes it a robust measure of spread. The IQR has several important advantages. First, it is much less sensitive to outliers compared to the range, since it ignores the extreme values in the tails of the distribution. Second, the IQR focuses on the central tendency of the data, giving us insight into how the typical values are spread around the median. Finally, the IQR is particularly useful for identifying the spread of typical values, making it an excellent complement to the median in describing grouped data. Now let's calculate the IQR using the quartile values we determined in the previous section. We found that Q1 equals 45.5 and Q3 equals 74.5. Using the IQR formula, we substitute our values. IQR equals Q3 minus Q1, which gives us 74.5 minus 45.5. Performing this calculation, we get an IQR of 29.0. This means that the middle 50% of our data spans a range of 29 units. Our calculated IQR of 29.0 provides valuable insights about our data distribution. It tells us that the middle 50% of data values span 29 units, indicating that the central values are relatively close together with moderate variability. Now we'll work through a complete example of calculating the interquartile range using the quartile values we found in our previous example. From our previous quartile calculations, we found that Q1 equals 68.5 and Q3 equals 84.2. These represent the first and third quartiles of our exam score distribution. The interquartile range is calculated using the simple formula IQR equals Q3 minus Q1. This gives us the range of the middle 50% of our data. Step 1, we substitute our quartile values into the formula. IQR equals 84.2 minus 68.5. Step 2, we perform the subtraction. 84.2 minus 68.5 equals 15.7. Therefore, the IQR is 15.7. The IQR of 15.7 points tells us that the middle 50% of exam scores have a range of 15.7 points. This means the central half of students scored within a 15.7 point range on the exam, indicating the spread of the middle portion of our data. When working with group data in statistics, there are important trade-offs to consider. Understanding both the advantages and disadvantages helps us make informed decisions about when to use this approach. First, let's examine the advantages of using grouped data. There are three main benefits that make this approach valuable in statistical analysis. The first advantage is that grouped data simplifies large data sets. Instead of working with thousands of individual values, we can organize them into manageable intervals that reveal patterns more clearly. The second advantage is providing a summary view that highlights overall distribution patterns, making it easier to identify trends, central tendencies, and the shape of the data distribution. The third advantage is that grouped data works well when individual data points are not available, such as in published reports or historical data, where only frequency distributions are provided. Now let's examine the disadvantages of using grouped data. While grouping offers benefits, it also introduces several limitations that can affect the accuracy of our statistical analysis. The first major disadvantage is loss of precision. When we group data, we lose the exact values and can only work with intervals. This affects the accuracy of calculated statistics like the mean and standard deviation. The second disadvantage is grouping error, which occurs because we assume all values in an interval are located at the midpoint. This assumption can introduce systematic bias in our calculations. The third disadvantage is that grouping obscures finer details in the data. Important patterns, outliers, or specific values that might be crucial for analysis can be hidden within the intervals. In summary, grouped data offers valuable benefits for managing large data sets and providing clear overviews, but comes with trade-offs in precision and detail. The choice to use group data should depend on your specific analytical needs and the level of precision required for your conclusions. When working with group data, one of the most critical decisions is choosing the appropriate number of class intervals. Too few classes lose important details, while too many classes create unnecessary complexity. Sturge's rule provides a mathematical guideline for determining the optimal number of class intervals. This rule was developed by Herbert Sturges in 1926 and is widely used in statistical analysis. Let's work through a practical example. Suppose we have a dataset with 100 data points. We can use Sturge's rule to determine the optimal number of class intervals. While Sturge's rule provides a good starting point, it has important limitations. The rule assumes a normal distribution and may not work well for highly skewed data or very large data sets. Professional judgment is essential when choosing class intervals. Consider the nature of your data, the purpose of your analysis, and the audience for your results. Sturge's rule should be used as a guideline, not a rigid requirement. Skewness and kurtosis are important measures that help us understand the shape and distribution of our grouped data beyond just central tendency and spread. Skewness is a measure of asymmetry in a distribution. It tells us whether the data is evenly distributed around the center or if it leans more toward one side. We can visually assess skewness by looking at the shape of our histogram. A right-skewed distribution has a long tail extending to the right, with most data concentrated on the left side. A symmetric distribution has data evenly distributed around the center, creating a balanced shape with no obvious lean to either side. A left-skewed distribution has a long tail extending to the left, with most data concentrated on the right side. Now let's examine kurtosis, which measures the peakness or flatness of our distribution. High kurtosis indicates a distribution with a sharp, pronounced peak and heavy tails, meaning more extreme values. Normal kurtosis represents a moderate peak, similar to a standard bell curve distribution. Low kurtosis indicates a flatter distribution with a broader, less pronounced peak and lighter tails. While mathematical formulas exist to calculate precise skewness and kurtosis values for grouped data, visual inspection of histograms provides valuable conceptual understanding of your data's distribution shape and characteristics. Understanding these visual patterns helps you interpret your grouped data more effectively and make informed decisions about appropriate statistical methods for your analysis. Descriptive statistics for grouped data have numerous practical applications across many professional fields. Let's explore how different industries use these statistical methods to analyze and understand their data. In economics, grouped data statistics are essential for analyzing income distribution across populations. Economists use frequency distributions to understand wealth inequality and economic patterns. Public health professionals use grouped data to analyze age demographics and health outcomes. This helps in resource allocation, disease prevention planning, and understanding population health trends. Marketing professionals use grouped data statistics to understand customer behavior and create targeted campaigns. Customer segmentation based on spending patterns, demographics, and preferences drives business strategy. Social scientists rely heavily on grouped data statistics to analyze survey responses and understand social phenomena. This includes studying educational attainment, social attitudes, and behavioral patterns across different population groups. Across all these fields, group data statistics provide several key advantages. They simplify large data sets, reveal patterns and trends, enable meaningful comparisons between groups, and support evidence-based decision-making in professional settings. We have covered a comprehensive range of descriptive statistics for group data. Let's summarize the key concepts and their importance in data analysis. We began with the foundation of group data analysis: frequency distributions and class intervals. These tools help us organize large data sets into manageable, meaningful categories. Next, we explored measures of central tendency: mean, median, and mode. Each provides unique insights into the center of our data distribution, with specific formulas adapted for grouped data. We then examined measures of dispersion, variance, and standard deviation. These statistics reveal how spread out our data points are around the central value, providing crucial information about data variability. Position measures, including percentiles, quartiles, and interquartile range, help us understand data distribution and identify outliers. These tools are essential for comprehensive data analysis. Descriptive statistics for grouped data are invaluable when working with large data sets. They provide efficient summarization, reveal patterns, and enable meaningful comparisons across different data groups. To master these concepts, practice is essential. Apply these statistical measures to real-world data sets from your field of interest. Whether analyzing sales data, survey responses, or scientific measurements, these tools will provide valuable insights. Descriptive statistics for group data are powerful tools that transform raw information into meaningful insights. Continue exploring, practicing, and applying these concepts to unlock the stories hidden within your data.